Thank you for this day. Thank you for the gift of life. Thank you for enabling us all to attend this lesson. And oh Lord Father, please help others to join and help us as we are being taught by the teachers to understand and not to forget, and to keep whatever we are taught in our heads and to use the knowledge wisely and to excel in all our exams. Please give our teachers the strength to explain to everyone until they understand. In Jesus' name I pray, amen.
And thank you so much, Nashi. Good day.
Welcome,
we are still working on our police, and I want us to share a document. And I hope we discussed the single fixed pulley. We now want to move to what we refer to as the single movable pulley. Is that okay?
Excuse me, Mr. Sir.
Yes, sir. Yes, madam.
As Mr. Sir, I had like a connection issue, so I joined a bit late. So, sir, I was wondering, what exactly are we doing today?
We are doing machines, and we are going to move to the single fixed movable pulley.
Okay, thank you, sir.
And I hope you can see the notes.
Sir, yes, I can see them.
I'm sharing that document. We are not going to waste a lot of time. We want to move to the single movable pulley. Can you assist me? Can you put this one? Can you try to make an arrangement? Over you're discussing and take one. We can make arrangement. Is it practical? Apparatus. Can you help me or I arrange or I let me okay. So we need a police, we need the record stand from there and so on. If possible, sometimes. As we're trying to make arrangements for you to get at least an experience of a single movable pulley, I want someone to read for us the notes, and then I try to explain those notes. I'm requesting somebody quickly put up your arm if you want to carry us through. Kelly, your arm is up. Please do.
Should I start from the single movable pulley?
Yes.
Single movable pulley. It consists of one moving pulley. At equilibrium, if the effort applied to the free end of the rope is E, then the total upward force on the pulley is 2E, since two parts of rope support it. Therefore, thus L is equal to 2E, MA is equal to L over E, which is equal to 2E over E, forming 2. Therefore, mechanical advantage of a single movable pulley is mechanical advantage is equal to length over effort, load over effort, which is equal to 2T over T, forming 2. Velocity ratio of single movable pulley, VR is equal to distance moved by effort over distance moved by load, which is equal to 2x over x, making 2. Note: for every 1 meter moved by the effort, each section of the rope supporting the load offers a half of a meter. The system in figure 2 is this makes it more convenient since part of the operator's weight can form the effort E. VR is equal to 2.
Okay, Let us try to look at those notes, and I'm going to explain them. I'm going to remove the notes and try and so that I can enlarge the blackboard and explain the notes. Is that okay? I'm going to stop and share. We shall share those notes later. Let us now concentrate on the board. Is that okay?
Yes, teacher.
So, how much on the board can you see? Can you see here?
Yes. Yes.
Yes.
No.
Our single movable pulley. Is that okay? We have the same string. The strings must be very clear like that.
Excuse me, Mr. Sir.
Yes, please.
What's this weird diagram you're doing? What's it called?
What?
What's this diagram called? Like, what's it called? What machine is this?
It has a subheading. What is the subheading? Can
I
somebody tell us?
don't know. I'm not sure.
Yeah?
I never had the subheading.
We have the subheading. What is the subheading? It is single movable pulley.
Okay,
Okay?
thank you, sir.
Okay, now listen, we have a single string. One end of the string is fixed. The other end passes around a movable pulley, a single pulley that can be movable. It is always going to be moving. Now we are saying that we have our effort. This is our effort. And that effort. We have our load. This is our load. So the load has a weight. The weight of the load is always acting downwards. That is our weight of the load. Okay? Now, I told you that yesterday that there is always a tension in the string and there is another tension in the string. So, I want to look at the load first. Remember that when the system is moving, there is a downward force called the load, and there are two upward forces called the effort. Now, how many sections of tension are supporting the load?
2 sections.
How many sections? How many forces are supporting the load?
2. 2 sections.
There are how many? There is that tension and there is that tension. So how many are there?
There are 2.
So there is 2T. The upward force is equal to the downward force. And what is the downward force?
The load.
Load.
That's the load. Is that okay?
Yes,
So the tension is given by the two sections supporting the load, that there are two upward forces supporting the load. That's what we have. Now, when you look at the effort is balanced by a single, it is applied on only one string. So what will the effort be equal to? How many tensions will it be equal to?
1.
It will be 1 because you are only pulling one section of string. So the tension will be equal, the effort will be equal to a single tension. Now, if we look at mechanical advantage is always given as the ratio of what to what?
Load to effort.
Load to effort.
Load to effort. So where there is the load you put?
2T.
Where there is the effort you put?
T.
So what if these two are identical? What will make us mechanical advantage?
2.
So when you read mechanical advantage as 2, what does that mean? What do you interpret from the mechanical advantage of 2? Can somebody tell me the meaning of that? I am going to Mercy tell us, what does it mean? What information does that give you?
I think when you have a mechanical advantage of 2, you apply the effort half of the load.
The effort is always half of the load. Is that okay? The applied effort is only half of the load. Let us look at it carefully. The effort applied, we are making the effort, if I look at L over E is equal to 2, that implies that this, I can write that as 1. And if I cross multiply, I'll bring this to this way, L over 2 is equal to the effort. Meaning the effort that is applied will always be half of the load. So I use a less effort to lift a larger load. I don't know whether you get my point.
Yes, teacher.
So, which of these machines do you prefer? Do you prefer the single movable pulley or you prefer the single fixed pulley?
A single movable pulley.
Why?
Because we apply half of the load's effort.
What happens in the single fixed pulley?
We apply the same effort as the load.
Very beautiful. So the single movable pulley actually eases work because you use less effort to lift a larger load. I hope you are clear about that. So that's the mechanical advantage. We want to demonstrate for you. I don't know whether we can watch this on camera. I think you can see it here. Take off once. Can we see the system we are trying to put up? Can we see the little stand?
Yes. Yes, teacher.
This what is doing is fixing the pulley, and that's what we have. So one end of the pulley is fixed, and the other, this end passes over the pulley, and then this is our load. Do you see the load?
Yes.
Yes.
You see the load now. I hope you see the load better. Okay. So how many sections of string are supporting the load?
2 sections, teacher.
2 sections.
Is one section. They are all supporting that load. How many do we have?
2.
We have 2. And to the effort is applied here, you know, Mr. Kugoza. To how many strings is the effort applied?
1.
1. So the effort is equal to 1 tension. The load is equal to 2 tensions because there are 2 sections that are supporting it. I hope you get the idea. Now,
Yes,
whenever you lift up, what happens? Whenever you lift, what
The
happens?
load is carried.
The load is carried upwards. Is that okay? Now, I want you to observe something when I'm talking about the mechanical. Now, you listen, girls. Listen to something that we are going to explain again. I want you to look at Mr. Kugonza's arm, and you look at the movement of this side of the rope. Is that okay? Lower. So that they can see the hand. Do you see where the arm is?
Yes, teacher.
Okay, so you look at this section of string and you look at this side, you are going to be comparing. So lift, lift, lift. Do you see where the hand has gone?
Yes.
So what can you say about the distance moved by the effort and the distance moved by the load?
You're going higher.
The distance moved by the load is far much bigger than the distance moved by the load. Have you observed that?
Yes.
Have you observed that? Do we repeat that? Observe the movement of the arm, go down.
Yes, teacher, repeat.
Look at the load carefully and start lifting. So, what can you say about the movement? You see where Mr. Peter Kugoza's arm is already, and where the load is. So, what can you say? Which is the bigger distance?
The distance moved by the effort.
The distance moved by the effort is far much larger than the distance moved by the load. I think you have observed that. Is that okay?
Yes.
Now we are going to talk about velocity ratio because it compares the distance moved by the effort to the distance moved by the load. That is our velocity ratio. Are we clear, guys?
Yes.
Now I have arms that are up. Noela, Kansimire, what are you saying?
I wanted to ask, when you say that load is equals to 2t, are we using the condition for body to be equilibrium, the one that says that forces acting in one direction are equal to those acting in another direction?
Exactly. Thank you for simplifying it. The forces acting in one direction are equal to the forces acting in the other direction. That is true. Okay.
Yes.
Okay. Another Anichiro.
Teacher, I wanted to ask where the 2 comes from when you're getting the mechanical advantage of a single movable pulley. Is it because there are 2 strings which are supporting the load that gives us that 2?
Exactly. There are 2 sections of strings supporting the pulley. So there are 2 upward tensions supporting the load. And that's why we say that 2T is equal to the upward forces are equal to the downward forces. So there are 2 tensions pointing upwards, and the load is one force pointing downwards. So that's why we say 2T is equal to L.
Teacher, you say that tension is always acting in the opposite direction of the effort, but how come here the tension and the effort are acting in the same direction?
Okay, I told you I don't want to go so much deep into that, but I told you that these tensions are like this. Whenever a string is attached, there's a load attached. There's a tension there. There's a tension at this point there, because if you remove, what would be, you see where I am pointing? You see where I'm pointing? Yes. Point. Suppose the load was too big. Do you know that this one would break? The string would break from here.
Yes.
So at this point here, there is also a tension, and these 2 tensions are balancing each other. I think I talked about it the other time, that whenever there is an effort or something is trying to pull a string, at that point there will be a tension, but there will be another tension that is acting at the same point. Now listen, for example, I can do this. I can show you this. This is what we mean by tension. Do you see this string here?
Yes, teacher.
Okay, now what am I doing to the string?
You're stretching it.
You're
I am
pulling
pulling
it.
it. Now I've stretched it. Can you do the same? If you have anything, you can pull. And you tell me, what do you feel in this arm? What do you feel in this arm? And what do you feel in this arm?
You feel like as if they.
You feel like the string wants to escape away from this arm. Similarly,
Yes.
you feel that the string wants to escape away from this arm, isn't it?
Yes, teacher.
Yes.
So that implies that for this, now, let me ask you, is this string moving?
No.
No, but it is straight, isn't it?
Yes.
So whenever I try to pull in this direction, I hope you have seen the direction that I'm pulling in. At the point of contact, there will be an equal but opposite force opposing my motion. I hope you get the point. So at this point of contact, the moment I am applying the force in that direction, there will be a tension that will develop that is going to oppose that motion. I hope that is clear. So similarly, when I pull this side, there will be another tension that will be opposing that motion. So there are 2 tensions that are going to be acting in the opposite direction, but we don't show those 2 tensions for purposes of clarity, because this tension here at the top is not acting on the load, it is acting on the support. While this tension here is the one that is acting on the load. So what we do, we are not interested in that tension that is acting on the support. I'm interested in the tension that is supporting the load. So even here, since the effort is trying to pull the string from upwards, there will be another tension that is opposing the motion. So for this string, that effort will be opposed by that tension. That's why I'm saying that since there is only one effort, there is only single tension, and that's why it is equal to T. So that's what I'm trying to say. But these ones, we don't show them for purposes that we are going to have too many forces that are unnecessary. Am I making sense?
Yes.
The effort is always equal to the tension in the string. That is the truth, Cherop. Is that okay? And yes, Sanyu Namuga, it is true. This is the applying Newton's third law. For every action is an equal and opposite reaction. That is also true. Is that okay? I'm trying to answer to questions in the chat.
Yes, teacher.
Those are, I hope I have answered the questions in the chat. So can I now try to move on and explain the velocity ratio?
Yes.
Okay, let us move ahead. We have said, you have observed that the effort describes a bigger distance than the load. I think Mr. Gonza demonstrated that practically. Yes?
I haven't understood those calculations. Like, where does the 2 out of 1 come from?
Anybody who can assist me explain these calculations? What have we said?
The load is being supported by 2 parts of the string, while the effort is acting on
tensions. Continue, please.
while the effort is only acting on 1 part of the string.
So that's why we look at these upward forces 2T are equal to the load. That is for the load. Now, when we go to the effort, you apply the effort there. But this effort is being resisted by another tension because whenever I try to pull, the string is almost also escaping out from your hand. So we are saying that the effort is also equal to the tension in the string. So when we compare these two and we look at mechanical advantage, which is given by load over effort, we replace the load by 2T and the effort by a single T. These two cancel out and we get the mechanical advantage as 2. And somebody has said that what is the meaning of this? The meaning is that you need only half, the effort required is half the load. That's what it means. So you use a less effort to lift a load that is twice the effort you have applied. Is that okay, Paula?
So I haven't really understood.
Okay. How do I put it? Let's take it. Somebody help me because for me, I don't know I can put it. Now I'm at a standstill. I'm also stuck. Yeah? Because you have demonstrated, I don't know whether Paula, you watched the video or she didn't.
So which video?
Did you see what we demonstrated with Mr. Kugonza?
So yes, I saw it.
So did you see the 2 strings that I was showing you, which were supporting the effort?
Yes, sir.
We say that in each string there is a tension which is acting upward and supporting this effort. This load.
Yes.
So we have said the upward forces in the 2 sections of string are equal to the load they are supporting.
Okay.
And then we say that for the effort is attached to only one section of string.
Okay.
Meaning that the effort will be equal to only that tension in that string. So the load will be equal to twice the tension, the effort will be equal to the tension. So when you apply mechanical advantage as load over effort, we substitute for load using 2T, we substitute effort using T, and that reduces the mechanical advantage to 2.
Oh, okay. Thank you, sir.
Okay. Okay, now let's move to the velocity ratio. I hope you observe that we have said that when you try to lift this load, the load moves far farther. For example, this is what I'm going to demonstrate, that if my load, my effort was previously here, don't worry. This is my load. And I lifted the load from here to a new position through X centimeters. So this will also be X centimeters. I hope you observe that.
Yes.
Is that okay? So this section of, because it is the same string, now what will be the distance moved by the effort? The distance moved by the effort, why the effort moves a bigger distance, is a simple reason. There will be a distance here offered, which is 1x, and so this is that distance moved by the load is equal to x. But this is supported by two sections of string. So this is giving us an x, and this is also giving us an x. So the total distance moved by the effort will be this x here plus that x there. So how many x's do we get?
2x.
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 Is that okay?
Yes.
So we are taking the load from this part to that part. By the time it reaches this part, this section of string has offered you a distance. It has moved through a distance of x, and this has also moved through a distance of x. So the total distance moved by the effort will be that x plus that x, and that gives us 2x. So if you are looking at velocity ratio, which is the distance of the effort divided by the distance of the load, what do I substitute?
2x divided by x.
Divided by x. So what is the velocity ratio?
2.
Is that okay?
Yes, teacher.
So that is how we get the velocity ratio of a single movable pulley. Is that okay?
Teacher, no.
What is the no? You tell me where the no comes from. Let me carry you back, people. Did you see Mr. Kugonza's demonstration?
Yes.
What did we
And I understood. I understood the first one.
Which
But I
first
don't
one?
understand. Done
What was
before.
Mechanical advantage.
Yes.
Now we are talking about the velocity ratio. We demonstrated that the distance moved by the effort is always greater than the distance moved by the load. Did you see that?
Yes.
Now we are trying to explain the reason. That if I lift the load from this point here, point A, and I lift it to point B through a distance of B, that implies that this section has moved through X meters, and this section has also moved through X meters, but it is the same string. Is that okay?
Yes.
So while this side is reducing in length, this side is reducing in length, this side is increasing in length. But by how much? It will accept this, and it will also accept that x. That's why we are trying to say that total distance moved by the effort will be this x, that x there from here to here, plus this x from here to here. Those are the two x's that we get. That's why the effort moves a bigger distance than the load.
Okay, I've understood, teacher.
So each section of string will offer the same distance, same vertical distance. So you add up those sections and you get the total distance that will be moved by the effort. And now when you go to velocity ratio, it will be distance moved by the effort divided by distance moved by load, which is 2x divided by x. These two cancel, and you get the velocity ratio as 2. Is that clear?
Yes.
So that's the advantage of a single movable pulley. Now, can you tell me the disadvantage of this system, the single movable pulley? Why do you think it has a slight challenge? It could have a slight challenge. What is the advantage of the single fixed pulley? What advantage does it have? Those with your notes, what advantage does a single fixed pulley have?
It changes the direction of application of the effort.
And how suitable is the direction? What's the direction of the effort in the single fixed pulley?
Upwards. It's easier to go
Now,
upwards.
what's the direction of the single movable pulley?
Upwards.
So it is upwards. So suppose you are here, you are trying to grab this object, but this weight happens to be stronger than you. What do you think can happen?
You
Pardon?
You
Suppose
can't lift
you are
it.
here. Let me put it directly. At the construction site. Let me try to tell you what usually happens. Careless people, this is what they do. They are at a construction site. It doesn't matter. They are lifting sand using a single movable pulley. Maybe that is a load. Now they are dragging this rope and they are on this support here. So this man here is trying to lift this load, this rope here. Is that okay? Is that okay?
yes.
Okay. Now this is the load. The load is acting downwards. So this man is applying his effort there. Now suppose this load is very heavy. For it, it is always trying to go down. And it is heavier, it is stronger than this man. What do you think will happen?
You will fall.
Fall.
Fall?
You understand?
Yes.
So much as the single movable pulley makes you lift half the load, I mean twice the load, I hope you get the point. The problem is, the challenge is with its direction of operation, the direction in which the effort is applied. Because if this happens to be a very big load compared to the effort you can apply, it can easily drag you down. So that the direction of the effort is not suitable. So there is an option, that is your diagram. How does that diagram work? This is what we do. Get your single movable pulley, and then you pass it over a fixed pulley. What have you done? Can you tell me what you have done?
You have changed the direction of.
You have changed the direction, but you have not changed the tension. Is that okay?
Yes.
So here, your effort is still T because it is applied to one section of the string, but your load is equal to what?
T.
To T. And therefore your mechanical advantage is still
2
over 2 altogether.
Yes, teacher.
And still your velocity ratio will remain 2. The same 2. So we don't use this system like this, we prefer to use it like this. Because by using like this is a safer direction to use, because you're already supported on the ground. I hope you get a point.
Yes.
So the system you see in your diagram is still working like a single movable pulley, because the load is attached to a single movable pulley. Is that clear, girls?
Yes.
Okay. That's what I can say about the single movable pulley. Unless there is a question, Noella.
My question is for this third diagram where you've joined the single movable pulley to the single fixed pulley. Now if you can see, there are 3 ropes, and okay, it's 1 rope, but like it's now in 3, like it's divided into 3 parts. The 2 parts on the single movable, and then the 1 part on the single fixed, and then doesn't that make them 3 tensions?
No, they are not 3. Because there are only 2 that are supporting the load. The load is only supported by 2. Altogether, this load here is only supported by 2 strings because it is attached to a single movable pulley. Now, what you do, this rope here, instead of you lifting it up, you change the direction, because this single fixed pulley can only change the direction, and you make the direction suitable. So that instead of dragging the effort being applied upwards, it is now being applied downwards. That's the advantage of a single fixed pulley. So you have used the same two systems, single movable and single fixed. One, to obtain a suitable direction, but two, to lift a heavier load. I don't know if that's making sense.
Yes.
Linda, I call you. I am in a class. Let me call you later. Okay. Okay. I hope that has been obtained. This system here simply offers you a better option by changing the direction of the effort, but still offering you the advantage of a single movable pulley of applying half the effort to lift the load. That is it. I hope that is clear. Joanna,
Yes.
anything you're saying? Are you okay?
Oh, no.
Okay. So that is our single movable pulley and the way it can be improved. This is the improvement. Are we together, people? Okay, we are going to move to the block, tackle and lock. Listen, can you give me some 30 minutes? Can you give me some 30 minutes in Kukubili? Okay. Okay, please share. Now we start on the blocks and tackle. Block and tackle. Who's ready? Okay. All right, now we're going to talk about the block and tackle pulley system. Can somebody read for us what these notes that Mr. Senjebe has shared with us? Daniela. Hello, Daniela.
Block and tackle single pulley system. It consists of two or more pulleys in two blocks mounted independently.
Please, those whose microphones are not muted, can you mute your microphones? Somebody whose mic is not muted. It's only Akelo Daniela speaking.
Block and tackle single pulley system. It consists of two or more pulleys in two blocks mounted independently on the same axle. One block is fixed and the other is moving. The load is fixed on the lower movable block. The upper fixed block has a number of pulleys as stated below in comparison with the lower movable block. When the total number of pulleys in the system is even, then the number of pulleys in the upper block is equal to the number of pulleys in the lower block. When the total number of the pulleys in the system is odd, then the number of the pulleys in the upper fixed block exceeds the number of the pulleys in the lower movable block by 1.
Okay, thank you very much for reading. Let me see. Okay, now, for example, this diagram that you see here, this is the block and tackle pulley system. How many pulleys do you see?
Two.
Pulleys. Now, there are two, we talked about two blocks. There is the upper block and the lower one. Which one is fixed?
The upper one.
This upper pulley you can see cannot move. This lower pulley can move. Similar to the case of the case we have just looked at of a single movable pulley. So, but now we
So in this case, we have two pulleys, and the string passes over the lower pulley and then also over the upper pulley, and so the effort is applied at this point. Okay. If you look at this scenario here, the number of pulleys in the lower block is equal to the number of pulleys in the upper block. There is one for each. What about in the second diagram here?
3 pulleys.
There are 3 pulleys. Okay.
2 up, 1.
2 up and 2 and 1 down, right?
Yes.
And yes. Then what about this? How
4
many?
pulleys.
There are 4 pulleys. How many in the upper block?
2.
2.
2. And in the lower?
2.
2.
There are 2 also. So we are going to, for each of these pulleys, we're going to look at the mechanical advantage. We are going to look at what mechanical advantage it is, and we're going to also see how we can determine the velocity ratio for each of those pulley systems. Okay. There was something to mention about the total number of pulleys in the system being even. So is this one even or odd?
Even.
Even. So if the number is even, then you can say the number of pulleys in the upper block is equal to the number of pulleys in the lower block. Yes. And then this one?
Odd.
Odd. So yes. So there are more blocks in the upper than in the lower. 2 against 1. Here, even or odd?
Even.
Even. Okay. So all those the total number of pulleys is even in each of those 2 systems. Now, in the real sense, actually, the pulleys are not this way, the way you see them here, but they are actually side by side. But for simplicity purposes, they are drawn this way, so that the one pulley is drawn below the other. Okay. But in the real, in the practical sense of it, these pulleys are actually parallel to one another. They are near each other, like that. Now, if you wish now, the velocity ratio for a system like this can be determined by counting the number of pulley, the strings supporting the lower block. How many strings here are supporting this lower block?
2.
There are 2. Okay. So that is equivalent to the velocity ratio of this system here. So you would say the velocity ratio is actually 2. Yes.
We are listening.
Go ahead with your question.
So it means that you have to set 3 divided by 2.
Okay, calculation. It is ST. That's why I'm trying to get something practical so that I can see. Usually that's what happens. What touch color, we don't get the idea.
The calculations is a mechanical advantage that one. What if you actually have?
Excuse me, teacher.
Yes.
I guess this was just an observation, but I was wondering if if the block and tackle pulley system can be called the wheel and axle, because I remember in the definition for pulleys, we had a pulley is a groove drill mounted on a block, and then a block and tackle single pulley system. It's mounted independently on the same axle. So can that?
No, we can't call it the wheel and axle. We actually have another machine called by the same name. The wheel and axle. machine. So we will discuss that one separately. We just keep calling this, you have to call this the block and tackle pulley system.
Okay.
So I was saying, so I was saying that one easy way of determining the velocity ratio is by looking at the number of strings supporting the lower block. Okay, when you look at this one, how many strings are supporting this lower block?
Three.
Three. One, two, three. Those three parts of the string are supporting this lower block. So the velocity ratio is 3. What about this?
4.
There are 4 parts of that string which are supporting the lower block. So the velocity ratio is 4. The mechanical advantage can actually be calculated if you know the effort and the load that is being lifted and the effort. So it is still the ratio of the load to the effort. So if we know the actual figures of what load, what effort has been applied, then you can calculate the mechanical advantage. Sometimes at this point where the effort is applied, as if you are doing it in a practical way, then we can attach a spring and that will give you the actual effort which you are applying. A spring balance. You know a spring balance? What is it used to do?
To weigh.
To weigh? To measure what?
Mass.
To measure mass. Spring balance.
Weigh mass.
It's not used to measure mass.
Spring balance is
certain objects.
It is used to measure weight.
Yes.
Weight of an object, to determine the weight. So if we want to measure the weight, this effort applied, you can attach a spring balance to this part of the string, and when you pull, it means that you can read from the scale to determine the effort applied. And these loads here, sometimes the load can be of a known weight. If you are using the standard value figures here, like the grams we have in the lab, you can determine their weight, the weight. Okay, if you're using the masses in the lab. Okay, but if you're using a different type of mass like this one I was using earlier, then this weight also can be determined. Okay, also by a spring balance or by our other weighing scales.
Hold on, girls. We want to do a very simple demonstration, but just give us a few minutes. We must only load it. You point to the camera.
So I'd like you to see this.
Okay. Can you see? Let me lower it. Can you see this pulley system?
Yes, teacher.
Yeah.
Yeah.
How many pulleys are in it?
Three.
There are three. Two in this is what they call the upper fixed block. This is the lower movable block. If you see the movable block moves with the load, do you observe that?
Yes. Yes, teacher.
Now let us look at, do you see where my fingers are?
Yes.
Yes.
That is the effort. The effort pulls one string. Is that okay?
Yes, teacher.
This is the same string passing over the whole system. Now, this system here, the effort is applied to the one section of the string. So the effort is equal to one tension. Is that clear?
Yes.
Yes, teacher.
Now, if I look at the load, this is our load. I hope you observe that.
Yes.
How many sections of string are supporting the load? Can we count?
1,
Followed
2,
by
3.
how many tensions are supporting the load?
3.
There are
3 tensions.
Okay. So there are
Yes,
three. By
teacher.
counting 1, 2, 3. Number 1, 2, 3 gives you the velocity ratio. Is that okay?
3. Yes,
By
teacher.
counting 1, 2, 3, number of sections supporting the load, that is the velocity ratio of this system. You can also equate it to counting the number of pulleys. How many are they?
3. There are 3.
There are 3. But it is always safer to count the number of sections supporting the lower load. That is usually the velocity ratio. Is that okay?
Yes, teacher.
Okay. Number 2. We are going to look at the velocity ratio. Okay. I hope that is better. Is that okay?
Yes, teacher.
Now, girls, look very carefully. Look at the distance. Look at the distance moved by the effort and the distance moved by the load. Is that okay? I am starting from here. I hope you can see the load still. Can you?
Yes.
Okay. Now observe the distance moved by the load as it is moving upwards, and observe the distance moved by this effort. I'm dragging. Which of the two has moved a bigger distance? Is it the effort? It is the effort. Is that okay?
Yes, teacher.
Now, each string is raising by 1x, 2x, 3x. Is that okay?
Yes, teacher.
The load has moved up a distance of x, while the effort has moved it through how many x's?
3x.
3x.
What is the velocity ratio?
3.
3.
3. Is that clear?
Yes, teacher.
So we discover that this system here has a velocity ratio of 3, and we can obtain that velocity ratio by simply counting the sections of string supporting the load. So if we arrange another system which has a 4, always simply count the section of
The
string
sections of the string supporting the load.
That is the velocity
Ratio.
for a block and tackle system. I hope that is clear.
Yes, teacher.
Now, the mechanical advantage may be less than 3. It may not be exactly 3. Can somebody tell me why?
Because of friction.
Because of friction in the movable parts of the pulley. Number 2, do you know that this pulley system also has this weight?
Yes.
Now, what is my purpose? Is it to lift this pulley or to lift this block?
To lift the block.
But by lifting of the block, what happens?
Yeah,
Also lifting the pulley.
I am also lifting the pulley. Is that okay? So
Yes.
when we discover that, I am also doing work in lifting this movable part of the system, of the machine. Is that okay?
Yes, teacher.
So I have
I can't hear you.
two challenges. One, is that okay? So that is why mechanical advantage is always maybe less than, maybe less than 3. Are we okay, girls?
Yes.
Yes, teacher.
Teacher, please
Okay.
remember to put the recording.
What?
She's asking if you can put the recordings on Google Classroom.
Recording is done by Mr. You are always asking for recordings, but I told you the person who is in charge of recordings. Who is that one?
Dove.
Who is
It's me.
that is Mr. Batu. This is S2. It is Mr. Batu. Me, I'm only here to teach. I'm not here to make recordings. Is that okay?
Yes, teacher.
Just be attentive.
So when you ask me for recording,
The recordings should not be
you
asked by
always divide
people who are
your-
present. They are supposed to help those who are not here.
I hope you get the idea. So, girls, that is our block.
I have bad network.
Mr. Bato, inbox Mr. Bato. You all have Mr. Bato's connection. I mean, phone. You know his contact. Is that okay?
Yes, teacher.
His hand is